the topic is more towards uncertainty-aware CBF, safety features, especially in autonomous systems in aerospace. So this is the outline of my talk, introduction, and then I'll discuss about safety challenges in aerospace. And then two major works I conducted over past 1 month. You can challenge me a lot, hopefully. And then I'll conclude actually this talk, and then we'll discuss about future work. By the way, I just completed this preparation of the slides this morning. So no way this is very complete, but I'll try my best. As I've been introduced, I'm working in KAIST and also adjunct professor at Cranfield University. And I'm leading a lab called Autonomous and Intelligent Systems. And my research topic is I'm very much interested in flying these aircrafts in challenging environments because it's more fun. Many of them, different types, because at the end, aerospace has two major axes, safety and efficiency. So in order to efficiency and safety, we need to connect them with the various different types of like systems and then network. So this is some topics I'm doing. Therefore, I do quite a lot of different things with my students and my research fellows, but very much focused in systems and control. So let's talk about what are the actual challenges in aerospace, I think. So we see more aerospace is become more autonomous, data-driven, AI-enabled, right? The question is actually in aerospace, we need to have like safety. Therefore, how to guarantee safety is key issue, right? We can't just actually run the AI. So therefore, I think safety critical autonomy becomes more and more important. But in reality, in aerospace, new areas which involves different types of uncertainties, different types of disturbances, and so on. So it's becoming more and more difficult. So the thesis is safety aerospace autonomy requires uncertainty-aware AI, not just AI-enabled optimization. So this is the kind of key thesis I have. I wanted to address this one, but before I address this one, I just checked why this is so difficult. We have limited data in aerospace, and all these safety critical events are very rare events, meaning that we have less data. Right? And how do we validate is a question mark still. And if we consider urban air mobility, meaning that we try to inject this aerospace in urban environments, then all of a sudden we have completely different types of uncertainties and disturbances and so on. So urban uncertainties are quite different from normal uncertainties we used to actually handle in civil aviation. And all this mixed up, making the problem so difficult. And we need to have some evidence generation and uncertainty-aware validation. So therefore, we might need to actually consider not only CBF, but uncertainty-aware CBF. This is the question. The technical core is, our system is, one of you actually asked, is nonlinear system. The types of the new aircraft we are actually discussing in advanced air mobility is quite different from normal fixed wing aircraft, which involves highly nonlinear system dynamics. And also the uncertainties we are handling is highly non-Gaussian. Pretty much all the method actually we are discussing is based on, anchored on, I would say, anchored on linear Gaussian assumption, which is not really valid in our case. So the key question is, how do we handle these difficulties, right? And therefore, the core question is, how can we, can safety control remains reliable when uncertainty is nonlinear and non-Gaussian? This is the key question I wanted to address, which I found so difficult, so I'm regretting. We'll see. So this is the talk roadwork and the motivation I just discussed. And then I'll talk about part one, which is called the spectral probability CBF, which I found very similar to the previous talk today. And second part is adaptive consensus safety filter. We just extended this to multiple agent case under the delayed communication uncertainty. And then I'll discuss about takeaway. So this is ongoing work, as I mentioned, to just 1 month work. And there are a lot of more things we have to do. So the first one is spectral probability control barrier function. I'm not sure, actually, this is really spectral probability control barrier function, but I'll discuss why this is like I'm thinking in this way. So as we have seen a lot today in the morning, so we have the very typical problem, CBF problem. Here I added one more condition, like some chance constraint, where we introduce a probabilistic guarantee certificate. Here, instead of having h of x bigger than or equal to 0, we have the probability of like this condition bigger than 1 minus or equal to 1 minus delta, which is type of chance constraint, because this is probabilistic, right? And here, because of all various actually different reasons, Gaussian assumptions are invalid, especially for this probabilistic constraint. This is a probability CBF condition, not merely a static chance constraint. Nonlinear dynamics and non-Gaussian noise distort the future state distribution, and evaluating the probability requires integration over nonlinear set evaluation sets. There are various ways you can handle this one, like introducing DRO or scenario-based actually QP and so on, but none of them is perfect. And of course, it's one type of different method, which is not perfect, but it's a new way of thinking, right? So let me introduce this one. So before actually we check this one, I checked actually whether or not there are already existing probabilistic CBF. And I found mainly there are two types. First one is a probabilistic CBF. The other one is data-driven. Probabilistic CBF will try to come up with a rigorous stochastic safety bound, where it relies on the non-dynamics and Gaussian noise assumption. So they try to come up with some sort of like a CBF, which is very robust against the probabilistic distributions. Second is data-driven CBF, merely focusing on actually getting CBF from the data we have, but it lacks robust guarantees under stochastic transitions. So the thing I wanted to come up with was something in between, a distribution aware and computational tractable probabilistic CBF QP formulation, but which can actually consider the nonlinearity and non-Gaussian distribution. So this is the need. How we can do this is we propose a two-stage actually approach. The first stage is called offline data-driven learning. Second is online convex QP. So what we try to do is we separate the problem into two stages. First, we try to learn all these like non-linear, non-convex, non-Gaussian things using the learning method, but not trying to learn CBF itself. We try to learn the surrogate function, which indicates the safety score, CBF safety score, and use this, because once we learn this one using the spectral kind of like a decomposition, we can make this one as a fine deterministic condition. And once this is translated, then we just use convex QP, which is very straightforward. So two stages: offline, map nonlinear non-Gaussian safety boundaries into a convex spectral distance. Second, which is based on the surrogate score. Second, online, we just solve a convex QP with the empirical margin. So the two stages. Here we need to have, for the offline learning, we need to have like three stages. First, dynamic lifting. We try to make nonlinear system to linear system in the lifted space using coupon operator. And second, we try to actually map this nonlinear non-Gaussian safety boundary into a convex spectral distance using SVM, CBF. And then because we approximate this one, we have residual. In order to have the rigorous mathematical guarantee, we have residual calibration, which can retain some mathematical guarantee. So that's three parts. So I'll discuss one by one. So as I mentioned to you, first we are using coupon operator in order to make a nonlinear system linearized. And how does this work is we can use coupon operator, which uses the observable, which is function of state. And this function of state has a transition, transition, which is coupon operation. and therefore we can actually lift this state into psi. From the observer state, we can have, which is a linear operator. We can, from the linear operator, we can define the infinite dimension function space. And because this is infinite dimension function space, we can make it linear. The problem is this is infinite dimension function space. We need to have practical method to approximate this space with the finite dimension features, which is a bit like cumbersome, I found. And for the applied learning, what we can do is exactly the same for our case. This is kind of like a concept illustration indicating how nonlinear dynamics can be linear dynamics in higher dimension. This is not exact because, as I mentioned here, it's an infinite function space, infinite dimension function space. But like a 2D, if you just like this, lift this one into 3D, maybe it's a linear space. This is the coupon operator concept. So here we use random Fourier features to generate the finite dimension spectral observables, function of state, and using EDMM-based, which is extension dynamics mode decomposition, we can load A and B after having distribution embedding. And from this lifted up space, the resultant system dynamics becomes this linear lift prediction for the embedded distribution of the original observables. So we have so linearized actually system dynamics from nonlinear distribution. Once we have this one, then we can actually try to learn the surrogate score, which is like learning the geometry of the CBF valid set in the chosen feature space instead of directly learning CBF. What it means is if we have like the CBF condition imposed, then depending on the state and U, we can actually define the get the data, which has the label, labeling safe set and unsafe set. So we have this difference, and from this difference, we can have the label. If the zeroing CBF condition is satisfied, then it means a +1. If this is not, then it's -1. Then once, and this is highly nonlinear dynamics. So what we do is we lift this space in, like we did for the nonlinear dynamics, using the same observables in order to make this condition as a linear condition. So we lift it. Once we lift it, we learn this zero level set where this condition becomes equal to 0. And this becomes a linear space. From this linear space, we can actually now get the CBF score. If this is unsafe, then it's equal to 0. If this is safe, then from this zero level set, we get the distance, and say the distance is the CBF score. So we can get this one. And once we learn this one, we can use this one as actually the let's say the affine deterministic constraint. But because we approximated this one using SVM and we also used the coupon operator, there is some residual, there are some errors. And if we don't consider the errors in designing this one, then the results will violate the safety condition. So therefore, we incorporated the two errors. First, from the SVM residual, the maximum distance of the force data. So we just check all this, like check the condition, and then check all the data, unsafe data, and find the maximum distance, which provides a force distance, and then define this one as M SVM. And also from the coupon operator, we just get the 1 minus delta quantile and define this 1 minus delta quantile as mu, and the lowest margin is the summation of these two errors. And what we can do is from this expectation of the hyperset, this expectation should be bigger than or equal to the robust margin, which is denoted as MR. Once if this condition is satisfied, then we say this is safe. Originally, if there was no margin, it should be equal to bigger than 0. Now we have the MR condition. the resultant spectral CBF QP formulation becomes like a minimum of the square of the distance from the nominal input, such that this condition is satisfied. So this condition is the original probabilistic stochastic control barrier function constraint. And the message is probabilistic safety control problem turns into a just convex QP structure. So now we can solve this QP as deterministic, any other QP solvers which can solve deterministic. So this is the result we have. And here, I don't know if you're able to see, so I can just zoom in a bit. The example we took is a very simple inverted pendulum case, where we define the safe set as plus 30 and minus 30 degrees of the inverted angle. And if we apply the nominal RQR, which is the nominal controller we are trying to follow, then certainly we'll see this actually violates the safety condition. But if we use deterministic CBF without considering the probabilistic CBF condition, then as you can see, this actually violates the condition, physical limit. And when we use a spectral CBF, the proposed method, we'll see this actually never violates the condition. Nonetheless, the margin, the actual distance from the actual output from the physical limit is somehow conservative. So why is it the case is that we found this is because there are certain errors. I just mentioned SVM induces error in learning, and also the coupon operator induces the error, and so on. So this becomes a little bit conservative. So we checked actually the conservatism of this proposed method with the DRO and scenario MPC. It's less conservative, but still it's quite conservative. So something we try to we need to address. Theorem, theoretically, if we have this condition satisfied, which is the deterministic converted condition from the probabilistic CBF condition, then we have this probabilistic chance constraint satisfied. Theoretically, we can guarantee this. This is a very straightforward proof. But the key contribution of this approach is we learn a spectral surrogate of the CBF value safe evolution condition instead of learning CBF itself. And we convert this non-Gaussian probabilistic invariance into a deterministic spectral constraint. Then we can actually easily solve this online QP. And we combine SVM boundary error and coupon predictor error into one calibrated margin MR, which is linear, which makes the problem so easy to solve. And it enables real-time safety filtering through an affine QP constraint. So this is the key contribution. The limitation, there are a couple of limitations I hit. The first one is it highly depend on the learning efficiency. Second, it's just still, I think, vulnerable to the distribution shift. So therefore, we need to actually find a way how we can address this one. So within a couple of weeks, this was okay. And then we wanted to move to originally I wanted to discuss about the multi-agent CBF. So I had to come up with multi-agent CBF. How I did was, again, some chance constraint safety. So here we have collision avoidance, multi-agent systems, where we need to satisfy the probability of collision avoidance is bigger than or equal to 1 minus alpha is chance constraint, right? For all for each agent I, with respect to all the other agents, which is neighbor of the ith agent. This is the pairwise chance constraint. And again, if we consider all these system dynamics and non-Gaussian distribution, this becomes non-convex pairwise chance constraint, analytically intractable. Time varying and stochastic communication delay, we don't know exact PJ because of the time delay and the uncertainties and so on. So this becomes non-Gaussian uncertainty. Information asymmetry from stall states is inconsistent local safety sets. And naive robustness, which we typically assume, leads to the conservatism. So the core question I wanted to address was how can we guarantee multi-UAV safety under non-Gaussian uncertainty, mainly induced by the communication delay, while reducing the conservatism. There are a couple of methods already proposed, but how do we reduce the conservatism is the main problem I wanted to handle. And therefore, we did some literature survey, and we found there are trilemma of this multi-agent safety. The three main objectives we try to achieve is safety first, obviously. Second, online tractability. We need to have like an online tractable solution, and also low conservatism. Right? We want to make actually this the control invariance set as close as possible to the true invariance set. So therefore, these are the three. But achieving three is almost impossible. So here you have like some method achieving these two, like safety and online tractability, and some method achieving safety and low conservatism, and online tractability and low conservatism, but not robust, and so on. So what we thought initially was robust CBF MPC seems like one good baseline. So we wanted to bring this one down to low conservatism, while maintaining safety and online tractability. So just push this one to low conservatism. That's what we wanted to have. And the core issue with this one is the chance constraint. We have, what we want to do is we want to guarantee true pairwise safety, meaning that the distance between the ith agent and jth agent pairwise should be bigger than the safety distance. Here, this is safety distance. And the probability of this, the safety condition should be bigger than or equal to 1 minus alpha, which is the chance constraint. And like geometrically, what it means is if we have the PJ here, the location of the jth agent, and PIs try to avoid this collision with this jth agent, then we have the safety set. And also the distance ith agent is going to use in order to avoid, it has a certain error, which is denoted as beta. So therefore, from this position, the predicted position, we need to add these like safety margins and have this safety region and avoid this safety region. So this is the condition we have. And in order to do that, what we can do is if uncertain quantification condition satisfies as this probability constraint, as long as the controller condition, the distance between the ith agent and the predicted position of the jth agent is bigger than or equal to delta safe plus the uncertainty beta, then we can guarantee that this probability chance constraint is satisfied. So at the end, how do we have the UK condition satisfied? And then the controller guarantees this condition. Now, everything depends on this beta, right? How do we actually tightly quantify the beta, which is the uncertainty caused by mainly communication uncertainty we are shown here. So how to reduce this conservatism without sacrificing safety is the key question we try to answer. So again, we did actually two stages approach. One is offline and the second is online stage. In offline stage, what we try to do is we try to have calibrated the UQ model, meaning that we wanted to have this condition. We wanted to find this condition. Once this condition is found, then what we can do is we can use just online MPC implemented, like just deterministic MPC, because this is a QP problem. And then we can solve this one while distributing the beta among the agents. Right? This is the condition. So now, how do we actually first find the UQ condition satisfies? And the aim is to learn a valid but tighter uncertainty margin beta that satisfies this chance constraint UQ condition. So if we have the beta, which is big, then at the end, the actually margin, conservative margin, becomes larger compared to the tighter margin we have. So we can actually have a smaller detour, which is much more desirable. And how we can do this is we can first actually have the data generation, which indicates the safety of the relative distance. If this is like a safe, then we say this is y is actually plus some value. If this is unsatisfied, we say this is 0. And from this one, from the condition, we can actually learn the y from the input data, which consists of the time delay and the relative dynamics, motion information. And once we learn this one using QP, visual learning, then we can get the quantile information. We can use actually Gaussian quantile calibration. But because this is non-Gaussian, using the Gaussian quantile is not really accurate. What we can do is we can use conformal quantile calibration, which provides much better, tighter margin calibration. So if we use QP quantile, beta can be learned from the QP. Here, Q is quantile we obtained from Gaussian process, but we can use actually this as CP. And this is the result. If you just slightly zoom in. So here, the actual GT error is this black dotted line, and the result from GP is this orange shade, and CP is the cyan colorish shade. And as you can see, GP area is far away from the ground truth, whereas CP provides actually a much tighter bound compared to the GP area. So therefore, from using this CP calibrated UQ, we can find actually tighter beta empirical conformal quantile, which is great. So now second part is how do we allocate the safety responsibility? Why this is important is illustrated in this simple figure. So if we have two agents, I and J, and try to meet this safety constraint at the same time without negotiating, what it does is in the actual physical domain, if we have the safety margin, right, inflated safety margin, this agent I should like locate its heading velocity direction outside, pointing outside this region, right? Then it's safe. For the agent J, it's the same. If its heading direction is out of this dangerous region, then it's safe. But to do actually exact the same, same behavior, so this is unnecessary. If it's coordinated, then what it does is in extreme case, J doesn't do anything. Agent I just try to avoid the collision, which just align the heading from current to this heading direction and just avoid, just get out of this dangerous region. So by doing this, by coordinating, redistributing beta, we can make not this is happening, and we just guarantee that this is much tighter. Right? So pairwise safety, less duplicated correction is beneficial. And the question is, how do we do this? So first, in order to do that, we need to define CBF. In previous talks, we discussed about how to define CBF. But for me, I just simply defined a very simple CBF function, a higher order CBF function. So here, the CBF condition is this distance between the agent I and the predicted J distance should be bigger than or equal to delta psi plus beta, which is the error in position. And the CBF is simply meeting this positive, non-negative, right? And then because it doesn't contain the control input directly, we can use a higher order robust CBF condition. Just differentiate this one until we get the input. And then just convert this one to the control fine safety constraint. We have this constraint. Here, G is the estimated and precise estimated because we have uncertainties. Now, if we just look at how this is formed, then the control of fine condition derived from the high order robust CBF is meeting this equation. Here, psi hat is the estimated, actually, the control barrier function margin, but it consists of the original the margin minus the conservative margin because we introduced the beta, plus some kinematic error because it's a high order dynamics. It introduces some budget, which is induced from the kinematic error. Now, this works in a good way because we are adding certain conservatism. So this is the plus margin because it's a minus. But kinematics, because of the system dynamics, it's introducing negative margin here. Typically, if it's uncoordinated, it's just simply actually try to make this condition satisfied, push ahead. But here, instead of just meeting both of them, meeting these two conditions, what we propose is we can reduce this psi ij by adding the weighting function omega ij to each agent, and omega ij allocate agents' eyes responsibility. Instead of like making all the agents fully responsible, we're just like allocating less responsibility to each agent, but while satisfying the safety condition. But why we can do this is it's very simple. If we just multiply omega ij here and omega ji, and then just combine them together, then it becomes beta ij. By just having omega ij plus omega ji equal to 1, then actually we can have the original condition satisfied. Plus we can consider margin. So the key idea is how do we actually have the same safety goal, allocate the correction. This is the key question we have. And centralized formulation can be now reformulated as this. So we have the original control barrier function, objective function, plus this condition, the shared responsibility should be equal to 1. And plus we have the affine control affine condition derived from the control barrier function, the coupled constraint, and u. And the scaled augmented Lagrangian function can be converted into this simple equation. Now we can use consensus ADMM because this is distributive. First, the primary updates try to find the best u and w, and consensus update to try to constrain w, actually meet the constraints. And then dual update is updating because we need to take into account how this condition is satisfied. So dual update can be achieved in this way. So now this is the result. If we see how this works compared to the other method, here is the result. We implemented this approach for the case where we have 8 UAVs and try to cross. And the delta safety is equal to 3.0 meters, so 3 meters away shoot. And we compare this method with the baseline safety filter without uncertainty quantification, and consensus safety filter where WD is equal to 0.5, just simply allocating this shared responsibility half to each agent. And then we have the adaptive consensus safety filter, which we propose. And as you can see, the adaptive consensus safety filter is the closest, is not violating safety, yet this is very close to the safety distance. Whereas other approach where we don't use uncertainty quantification, the safety is far away from the 3.0. And also consensus safety filter with the same responsibility is reducing the conservatism, but still have a very conservative algorithm. So when we actually check the performance, this is providing, in terms of the various different like matrices, is providing the best performance against benchmark algorithms. And theorem, we can actually prove that safety certificate can be actually guaranteed under adaptive consensus. So as long as the net robustness reserve, which is induced by introducing the beta, which is the error induced by communication, and the capture relative motion CBF residual induced by the kinematics is bigger than or equal to this model mismatch penalty under allocation, then this condition is satisfied. So we can design gamma or rho to meet this condition, also we have to actually constrain Wij, not making this one too big. So there are a couple of like ways we can design gamma and W. And allocation of this responsibility is making the algorithm less conservative while meeting the safety. So these are the kind of like a trajectory of the two proposed benchmark and the proposed algorithm. Yeah, as you can see, it's like very smooth. Whereas when we use just a safety conservatism, without uncertainty quantification, then it produces a very like non physically possible trajectory. Okay. So in conclusion, I presented two uncertainty-aware CBF developments toward aerospace autonomy. Aerospace autonomy. I didn't really discuss about aerospace autonomy, but one is a probabilistic CBF foundation, spectral formulation for nonlinear, non-Gaussian uncertainty. Second, I addressed the multi-agent CBF extension, where we have adaptive consensus safety features under delayed communication. And both translate uncertainty-aware safety requirements into tractable online control constraint. So this becomes deterministic kind of QP or MPC problem, which we can easily solve. The results indicate reduced conservatism while retaining formal safety certificates. So what I tried to do was having the less conservative algorithm, but retaining the mathematical rigor. So that's something I tried under this non-Gaussian nonlinear case. And takeaways like uncertainty-aware CBFs provide a pathway from probabilistic safety foundations to cooperative autonomy. So we can extend this one. So in order to do that, there are more works to do. So we need to improve scalability of spectral uncertainty representation, because the performance highly depends on this uncertainty representation. And the residual error highly depends on this representation. So also, we need to apply the spectral CBF to practical aerospace application. Also, combining with the how to design CBF, obviously. And we need to extend the probabilistic safety guarantees under rare events and distribution shift. And we also need to develop adaptive tuning, those for gamma and rho, and allocating weights. As I touched at the last slide of the second part. And we need to also analyze large-scale behavior for dense UAV AM traffic networks and validate using hardware expense and high-fidelity aerospace simulation. So the long-term goal is we try to come up with a real-time certifier of the CBF safety features for safety-critical aerospace autonomy, which is quite ambitious, considering I've done this only for 1 month. But this is the direction I think we need to go with this. I think this is it for appendixes. So thank you very much. Any question?
Great. Well, I'm wondering how the first part,
so at the end, here what we used was this random Fury feature, assuming that this reflects the real like a basis function. But the observable, depending on how you define the observables, when you implement the store integration, the residual error can be constrained, depending on how you define the observables. Right? So therefore, when we actually try to approximate the infinite function space into the finite function space, we can use less like observables, which can better represent the actual infinite space. And hence the error can be retained with actually less number of like the observable functions. But if this is not the case, although we chose 3,000 observables, basis actually function, 3,000, but the error was like much bigger than I wanted. But like depending on actually how you define this one, there are some other studies like discussing how to define these like observables. You can retain the error with the less number of like observables, and which will greatly improve the performance, and that's the basic direction. Yes. So when we, not correctly, but we set number of observers 1,000, 3,000, and 5,000. So we check the trend. Difficult to say I checked actually real trend, but it's kind of like somehow converging to a certain. But is it because of the actual physical limitation this Cooperative operator can achieve? Or is it because of the limitation of this, the basis function with observable we define? We are not 100% sure. But it has some conversion pattern.
I think the Cranfield from Cooperative, he has a recent paper on analyzing the on the gap between Cooperative representation and our field system on the dimensionality of the source, and it shows something like 1 over 10.
Where and
yes,
yeah, there's certain assumptions, yes. But that assume something we don't want to assume. Yeah, that's the hard part, yes. Yes.
It's very interesting. Although I will move on to pattern analysis. My question is on the representation. So when you list the original analysis in your linear one, right? How do the noise enter the system?
So it has, luckily, Cooperative operator has something very nice property. It has a dual, which is called the Panon provenience, actually. So therefore, you can actually simply just do this Cooperative operator and then get the kind of expectation. Then it becomes actually this probabilistic space. So using just a dual property, we can just simply do this.
And if you consider the model mismatch in the vector system, theoretical system, is it reasonable to just put the model mismatch into in of the noise?
That's a very good question. Yes and no. What we wanted to guarantee was the chance constraint, 1 minus data. So even though we do actually this mean, then we are guaranteeing that 1 minus data quanta will be staying within this boundary. But obviously there are certain cases which are not falling within this 1 minus data quanta, then it's not safe. So therefore, for our case, if we want to guarantee 1 minus data chance constraint, it's okay. But for heavy, very robust against all these cases, then this is not really. Yes. Yes, probably still, yeah.
I totally agree with that. They have lambda parameter. That was one. And I wonder if your possibility is that parameter at all.
It does. So therefore, we need to also find a way how to design this lambda. But as I briefly mentioned, the way we can actually do this is using this equation. So using this equation, I think we can do this. Right. Yeah.
It's related. I think yours is operating that parameter.
Yes. In not really 100% sure this can be generalized in general CBF, but for me, this is like a more multi-cooperative multi-agent. Yes.